Thank you for being here. Before starting, I'd like to ask, by show of hands, who of you works in security or has worked in security before? Oh, great. So I would say the majority of you work in security. All right, so my talk will be about hunting malicious injections using application real-time monitoring. And let's see what the hell is that. So before that, a little bit about me. So I'm Pedro Fortuna. I'm founder and CTO of JScrambler. Presently, I mostly work in application security, mostly around JavaScript and JavaScript code protection. But before, I've also worked, like 10 years ago, I started working with developing bot detection techniques, fraud detection, and all of that. And more recently, I've been paying a lot of attention to anything related to man-in-the-browser Trojans or malicious extensions or anything that ends up like injecting something in the client-side context in the browser. So the agenda for today will be, we'll start off by mentioning a couple of real-world examples. We're checking how the client-side integrity threat landscape looks like. Then we'll jump to the main topic of this talk, which is the new approach that we have developed that we call application real-time monitoring. And then we'll have a live demo, and it's basically it. So in late 2014, jQuery CDN was breached, and for a short amount of hours, every website that was loading jQuery directly from their CDN was basically serving the rig exploit kits to every end user going to those websites. So as I said, it only lasted a few hours, but can you imagine how many users were being hit by the rig exploit kit? It wasn't the first time that something like this happened, but to my recollection, it was probably the first time that we really started paying attention to this kind of threats. So, and back then, we said that we'll see more like this in the future, and today we know that this is true. And let's see other examples. So in the year after, in 2015, a man-in-the-browser attack hit like hundreds of banks across the world, and the attackers managed to steal roughly around 50 million US dollars. But what was worse about this attack is that it lasted 2 months between just they starting exfiltrating money from the end user's account and the takeoff of the bot. And we're talking about hundreds of banking websites. So a lot of people could have paid attention sooner, and probably the threat would be killed more quickly. And it didn't happen. Last year, a dependency was compromised, and websites like Equifax and TransUnion were affected by this. So basically, and what was happening, and I quote, a carousel of badness was being served to every end user of the affected websites. So the malicious code was either serving a fake survey to the end users to collect like their personal data, or was serving like a fake Flash plugin or even an exploit kit, and it was compromising the machines of the end users. This year in February, we have seen also a dependency. In this case, it was browser allowed, which is a plugin to read out loud the text of a website. So a few websites were hit by this compromise. So that basically the attackers they changed the library directly in the server of the third-party dependency, and they injected the CoinHive's library to use the end user's PC to mine cryptocurrencies. So among the websites that were attacked by this, you have the UK's ICO, which ironically is an institution that is meant to protect the privacy of UK citizens. So it was one website among 4,000 others, but you know how it works. You're going to talk about the most polemic cases, of course. In March, we saw a Man in the Browser campaign. Not only it was targeting financial institutions, but it also was targeting crypto exchanges. More precisely, it was attacking Coinbase and blockchain.info websites. And actually, this issue was discovered by a company named the Security Scorecard, and we actually reached out to them, and we ended up collaborating and doing like a deep analysis of what Trojan and the injections were doing in those crypto exchanges websites. And the result of that, we did a talk this year at DEF CON demonstrating how they work and what they were doing and what they could potentially be doing next if they evolve this type of threat. But one thing that caught our attention is that crypto exchanges are websites that usually use everything that you have at your disposal to protect the user's authentication. They are very worried with account takeovers. They use two-factor authentication. Everything that you do, they will send you an email just warning that you just did this to your account. Make sure that you are the guy doing it. So they use a lot of different techniques to prevent fraud and account takeovers. And despite that, the man in the browser was able to quite easily steal two-factor authentication tokens and manage to downgrade the security of these crypto exchanges and basically put the attacked accounts pretty wide open, and they could, if they wanted, they could very easily transfer out every funds of the attacked accounts. More recently, just last month, I think, and this is to show that we are not just talking about man in the browser or third-party components that have been tampered with. In this case, is an extension which the developer credentials were stolen, and they managed to push a modified malicious version of the extension. And if you know how it works, it's rolled out automatically, and everyone is updated at once, so it's very quick. And it only lasted like 4 or 5 hours, but it was enough to create a lot of damage, because this extension in particular, it has, I think it's 1.7 million users. Okay, so what it was doing, it was collecting the credentials and personal data and crypto keys, private keys from everyone using this extension. So if you and credentials from Gmail, Microsoft email accounts, and whatever and whatnot. So in 5 hours, I'm sure they managed to collect a lot of good stuff. Eventually, Google was tipped off. So this happened in Google Chrome web store. They were tipped off, or they discovered, and they took down the extension. And when they do that, basically the extension becomes disabled in every browser. So it's very quick to react. But the problem is, they are reacting. So they are not. It's very hard for extension stores to discover if some extension is malicious, especially because they rely on things like the reputation of the extension. And in this case, when you compromise an extension, basically the reputation up to that point is good, right? So it's not malicious. But we also know of many extensions that are malicious from day one. And it's very easy for them to not get caught by the initial screening from the browser web stores, so it's very easy. In particular, because it's easy for them not to do anything during a certain period or not have malicious code, and then they can just pull off malicious code at a certain date and start becoming malicious. So reputation-based screening is very hard. It requires someone to notice and report those in order for the threats to be mitigated. And this has been happening on and on, so it's a constant. Every day you see news like this. More recently, in the last couple of weeks, we have seen a rise in the number of attacks against e-commerce and also ticketing websites. And we believe that these attacks came from a group called MageGuard. So you might have bumped into a story or two about this group. So the first time they started attacking stuff, it was like 2 years ago. But very recently, they increased their activity. And for instance, they were able to collect around 40,000 credit card details from 40,000 users in Ticketmaster website. And it was even worse for British Airways. They managed to collect personal data and also financial data from 380,000 users. Yeah. Anyone flew in British Airways lately? Oh, one guy, two guys? Okay, just be warned. Okay, but the point is we have been paying attention to this. We have spending a lot of effort just passing the message along. And last year, to give you an example, we presented our own Trojan that we developed using a Chrome extension. So it's basically a hybrid between man-in-the-browser Trojan and a malicious extension. And what we managed to do, we managed to collect every piece of data that you can think of from websites. We managed to take screenshots. We managed to redirect users to the things like, let's say you go to Google and you search something, and we can actually redirect you to a different website. So you think that you are looking for some answer, and we can manipulate you and maybe make you believe a different thing. And we also were able to strip out or modify any security header in the traffic. So it means that we could disable CSP, we could disable basically anything that relies in headers. And this is just like a demonstration of what you can do. Nothing like this is like really new. It's just an educational thing for people to become more aware that this is happening. So this picture summarizes the attack vectors against client-side integrity. So starting off, you can have malicious or compromised third-party libraries. And for that, you should use vulnerability tracking to see if you are using components with known vulnerabilities. But of course, that doesn't work all the time because you have to know the vulnerabilities ahead of time. You can use sub-resource integrity, which basically allows you to add attributes to the tags with hashes, with the integrity checks of the scripts that you're loading. And if they are not right, the browser won't load the scripts. And you have content security policy, which allows you to specify policies and of what scripts you want to load. You're allowed to load from what domains. You can do nonce-based approval of certain scripts. You can do a lot. But as I said, many of the browser Trojans, for instance, they can strip out this information from the page before the browser actually computes these policies. You have malicious browser extensions. Of course, you have the browser stores have their own screening, their own blacklisting, but I've talked about this before. It constantly fails. You have antivirus. They can detect some forms of malicious code, but they are really very ineffective. And you basically have to rely on the end user not to shoot himself on the foot and be wary and basically try to understand if something is wrong and avoid doing it. You have man-in-the-browser Trojans, which, in my opinion, there's not really something brilliant that you can do. As a web application owner, you must, in my opinion, just assume that some devices will be compromised. So maybe you can prevent some from being compromised, but not all of them. So you have to have some sort of plan against that as well. And finally, you have the server breaches, or things like exploiting common vulnerabilities like XSS. And in this regard, you should do vulnerability scanning, pen testing, but as you know, it doesn't ensure you that you are finding every possible vulnerability. You can run your own bounty programs. You can use security headers to try to enforce the use of certain policies. But some will get through and eventually inject something into the context of the web page. So what are the main takeaways from this? Basically, that we are relying too much on third parties. So vulnerability tracking, you need the guys that are developing that to keep up with the rules, just update them as quick as they can, and all the researchers that are involved to keep up, like discovering things. Third parties, well, you shouldn't, in my opinion, you shouldn't load directly JavaScript from a third party. The best approach will be probably you need to download the dependency and just host it yourself, okay? But that doesn't protect you from being breached and the code being modified directly on your server. And also, it might be an inconvenience if the code is changing and you want to have your application updated. But in my opinion, you should do that still. You should host the version, because you don't want the third party to keep changing the application because they have a component of your application. You don't want them to change without you knowing, without you having the possibility of running your own testing, your security testing. So it's actually a good thing that you host the file yourself, because it allows you to have more control about the code that ends up running with your application. So we know that the browser extension stores, currently they do a very crappy job, and basically they tell you to your face. So you must not rely that these extension stores will protect your website from being like completely defaced or modified, and things like completely tricking the user into doing something. And you have to rely on the user not to install those malicious extensions, which we all know that will fail. Antiviruses are not efficient, and users get easily infected. So in a nutshell, we are relying too much in things that we do not control. And existing solutions also have their limitations. I mean, I'm the first guy to say you should use CSP, you should use HSTS or whatever. You should totally follow a defense-in-depth approach. But at the same time, if you do your threat modeling, if you do your analysis, you know that sometimes that's not enough, and you need to have a number of different strategies to catch the ones that are getting through. And these attacks, the examples that I've shown you, they are far too appealing for attackers, and we have seen these attacks increasing. So we better just assume that some injections will get through. And this reasoning just was the motivation for our work. We started developing this approach that we called application real-time monitoring. And initially, we asked ourselves, so if we cannot avoid injections, what can we do? Is can you have another way of trying to reduce or attenuate the problem if you cannot mitigate the problem 100%? And so we came up with this application real-time monitoring that I will explain to you in a second. But these were the requirements that we enumerated. So we were thinking about how to do this. And the first thing that we realized that we couldn't do this at the markup or file level. We couldn't check the integrity of things at the file or markup level. Because some of these threats, they only modify things afterwards. So after the page has been loaded, and maybe they will just wait out a minute or two before they modify the page. So it must be something that comes later and monitors the page continuously. Okay? So it must be in real time, because once the injection is made, maybe you only have a short amount of time to do something that will mitigate or attenuate the problem. If you just do something like 2 months after, maybe that's too late. So we aimed to do this in real time. It must be transparent, and this is not a strict requirement, it's just a convenience for the solution, because we didn't want users to have to install something in their own devices. We don't want extensions, we don't want any end user agents that you need to install. It must be transparent. And it must be scalable, and because potentially we are monitoring multiple websites, and each website can have like millions of requests per second. We don't really know, so it must be scalable, otherwise it won't work. And it must be precise in the sense that we all know that if you look at a web page, it's very lively, so it keeps changing, the DOM keeps changing, the user clicks things and things appear, so it's actually constantly mutating. So the ability of reporting what's important, it's, I would say, it's critical for this approach to work. Otherwise, it will be just a bunch of random noise that no one will bother to look at. So the approach basically monitors the DOM continuously for any injection or modification, and also checks for event handlers being modified. So if you have, let's say, a form, and you have a function that gets executed when you submit that form. So we call this event handlers, and they are frequently a target for malicious modification. Because it's a way to do a sort of man-in-the-middle kind of attack, because they just intercept the submission of the form, they execute their own codes, and then they collect what they need to collect, and then they just let it go through to the real destination URL. Also checks for modifications to JavaScript native API functions. So it's common for attackers to do this, because it's very easy and convenient for them to modify the behavior. Let's say that your form uses some sort of native function. They don't bother to analyze the code. They just poison that function and put themselves in the middle to be able to collect information. So, and it's a bit more stealthy for them to do that. It's not, so we also check for that. Once we pick up something, we send out notifications, and those notifications are used to trigger automated reactions. I will show you in more detail in a bit. So this is the general architecture of the solution. So we have the server and the client, and we have a client-side JavaScript agent. So this is one side of the solution. So you need to somehow deliver this JavaScript agent to your website. And this website continuously monitors the DOM and all the other stuff I mentioned for injections. It relies on the mutation of servers, which is an API that you have in the browser for just listening to changes to the DOM. So this is one of the things that it uses, but it also uses other mechanisms with different levels of sensitivity. We use checksums for certain parts of the page, and we also use poisoning detection using JavaScript capabilities. So once tampering is detected, notification is sent back to the other part of the system, which is the real-time monitoring backend. And this backend just processes the information, confirms that it's indeed, in fact, malicious modification, and the application optionally can implement this webhook it will receive in this webhook the final information, like regarding that incident. So using this information, they can just implement whatever reaction makes sense to them. So this is something that it's the application that does, because the solution itself, semantically, it doesn't need to know the specifics of the application. It doesn't need to know the policies that the organization uses. So it's really about sending real-time information of what's happening to the backend, and let the backend just implement policies on how to react. All right? So it's quite simple, actually. So it follows a whitelisting approach. So it's able to detect anything that's different, contrary to using a blacklisting approach, which we basically would need to anticipate what we are looking for. And like I said, it uses different levels of sensitivity, and this is important for the scalability requirement, because otherwise we would be flooded with different sorts of modifications of the page, and it would be impossible to deal with that. But this isn't enough. We also use some machine learning techniques to filter out what seems to be not malicious modifications of the page, and to distinguish those from normal modifications, we need to have a certain training period in the website just to learn what it does normally. It also supports signatures, so you can specify what you're looking for, and that's used for certain countermeasures. So when we conclude that on the client side, not on the back end, so if on the client side we conclude that we are definitely looking at a certain known injection or even uncertain, you can execute these countermeasures. The first one, we only do it if we are sure that it's really not a false positive, so it requires the signature. So we need to classify. Let's say we are looking for a certain man-in-the-browser injection. So we ship that with the agent, and the agent, if it does detect that signature, it can remove the injection on the spot. And all the other ones are generic. So you can tell the agent just to, if you find something, you can redirect to a certain URL. You can delete cookies, which effectively will kick the user out of the session, or you can execute some callback on the client side. So about the real-time alerts, just to mention a few examples that you could implement with this. Let's say we're talking about an online banking website. You could block the user account, like immediately. Let's say you detected the tampering to a login form. So you better assume that those credentials were captured. So one possible reaction on your side would be to just block that user account, or to contact the fraud department and warn off that they need to investigate and maybe contact the end user to tell him that his device might be infected, and for that reason we are blocking your account. Or you could raise the risk of the session and maybe even roll out different security measures dynamically. Let's say that you have a CAPTCHA that you want to serve. Let's say that you want to do some behavioral analysis on the client side, but you don't want to do that all the time for every session. You can have a dynamic situation where the finding an injection would trigger just serving more challenges to the client side. But this has a caveat. In order to do what we do, and remember that we are using JavaScript on the client side, which is by itself also exposed, we need to somehow have some sort of assurances, or at least make it harder for someone to interfere with our own JavaScript. So in order to do that, we are using polymorphic JavaScript obfuscation, which is also tamper resistant, so it's able to detect any modification to the code itself. And it detects when people are trying to debug that code specifically. And we recommend that this code, the agent, will be mixed together with the code of the application, so that the attacker won't easily know which part of the JavaScript code is the agent, which part is the normal code of the page. So this is about raising the bar, so you won't have like 100% assurances that this won't be defeated, but since it's polymorphic, you can basically have a completely different code from request to request, and it becomes very complex. It raises the attack costs, and usually when you do that to attackers, they just move to the next target because they are usually lazy and they go for the low-hanging fruit of things. Okay, so let's go to the live demo. All right, so for this demo, I will be using a dummy website, online banking website. All right. So let me load the website. Just let me prepare all the things. Okay. And this is the website. So one thing is going wrong already with this. And to prove you that, let me open the same website, but on a blank browser profile. So can you compare the two? What's the main difference? Can you tell me? Pretty obvious. It's the banner, right? So this one on the right side doesn't have a banner. And let me close this, and this one has. So what we are seeing here is just a regular banner. It's being loaded from the actual website. So remember, it isn't a phishing website, some sort of clone. It's the real website, and the modification is being done on top of that. So we are seeing a banner, and it's basically inviting the user to download a mobile app, which is fake. It isn't a real mobile application. And if we click one of the buttons, you are taken to a copycat of the Google's App Store, and which is really similar, but the only difference is instead of an install button, you have a download button. So once you click that, it's downloading an APK, which is obviously a malicious application. And remember that many people, they might run this on their phone. So once they download the APK, and if they have their settings allowing installation of APKs, they will end up just infecting themselves. And this is a good thing for the attacker, because probably he will be able to capture not only the desktop browser, but also their mobile browser as well. Okay, so now that you saw this, let me enter. This is the dashboard of the application real-time monitoring. So usually the user isn't seeing this, but I have to use the same computer, so I'm just putting this side by side. Obviously, as you can see, there's no threats detected so far because it isn't enabled yet. So this is what I'm going to do next. So I'm just editing the templates of the website. Don't worry if you are not seeing this correctly. I'm just uncommenting this script tag on the website. And I'm only doing this like this because this is a demo. So usually I wouldn't deploy the agent in such a way which is so easy to see that we can cut this line. And so this is just a proof of concept, all right? So everything is okay? Okay, all right. So let me restart the application. So this is the application of the virtual bank, okay? So I'm running this from my own PC as well. All right, so now I'm reloading the virtual bank application, and just a few seconds later, just pay attention to the banner, and afterwards, like a second later, to the dashboard on the back, right? All right, so what you just saw was real-time monitoring of the page. We had a signature for that particular injection, so we were able to do the countermeasure of self-healing the page. So we just removed the banner, and the information is correctly processed and passed on to the backend of the application. And once it's there, it can be sent to the webhook of the application code. So let me try to show this to you. Okay. So what we have here is a blacklisted fake mobile app banner that has been removed successfully. And what is interesting is that we can show you like the very little details of the injection. So this is the actual code that the user was seeing, which is sometimes hard to get from the application developer perspective because he knows what code he has served to the user, but he doesn't really know what code ended up executing on the client side. And this provides you to you, so you can see that. And this div element that you are seeing is basically the whole block of the banner. And you can see the whole details. You can see that it was using inline images, and you can see that it was linking to not Google, but Goggle, okay? It's silly, but it happens and usually works. And if it didn't work, the attacker could go even further and just like do DNS spoofing or whatever it needed to do in order to trick the user. So it's really hard to tell if you are a user and just watching the web application. But let me continue. So right now I'm about to log in. And I haven't even logged in yet. I'm already seeing new threats coming in. So what's going on here? So let's see. We have code poisoning. And let's see what this means. And what you are able to do is the onSubmit event has been tampered. And it's basically has been replaced. The whole function that gets executed once you log in, it was replaced by a function of the attacker. So this is basically collecting the credentials and exfiltrating them to another place. But remember, this is a demo. If it was a real case, then after we caught the banner, the whole session could be already modified. We could already be reacting just before even like letting the user log in. We could like not serve the login form at all if we wanted to. We just like block the user from using the website. And if we can start managing the context of that session from the first time that we see an injection. Let's proceed. Nonetheless, just log in. And this is the menu. Let's initiate a new transaction. Let me do, okay. A new threat is coming in. Another code poisoning. Actually, it's the same kind of injection, but this one is a little bit more juicy. So you can see what it's doing. It's very easy to read. It's collecting the original name of the transaction. And this is the function that only executes when I click submit. So I already filled up all the forms. So I'm collecting the original name, the original destination account number, and this is being kept in session storage, and I will explain why in a minute. And the whole thing is, the attacker is basically injecting its own destination account number in the form. So what the bank eventually will see on the back end will be the destination account number of the attacker, okay? Despite the user seeing the destination, the regular, non-tampered destination account number. So I'm doing a transaction to my landlord and submitting. So I know that I just got compromised and the transaction was modified. And here I'm in the confirmed transaction page, and we are seeing new threats coming in. Let's see what's happening. And basically what's happening is that the user, the attacker, sorry, is modifying information in the confirmation form so that I keep thinking that everything is normal. Like I keep seeing the name of my landlord, I keep seeing the destination account number, and all this information is being fetched from the session storage, and the attacker keeps modifying, so he keeps modifying the user experience as he goes along. And actually, it's a low-friction kind of attack because if you think about it, the user is using its own PC, it's using at a regular hour, logging in from a known geographical location, probably doing a transaction of a value that's not uncommon for him to do that. The only thing that's different is the destination account number. All right? And if it's a one-off transaction, it's almost impossible for the bank to flag it as being fraud. So this is definitely going to happen unless we stop that. All right, so let me just proceed. And again, the final details keeps being tampered because we want to go to do something else and keep thinking that everything is normal, everything is okay. All right? So this is it in terms of demo. This was just one example, one use case, banking, but I wanted to let you know a bit what other kinds of things that you can use this approach for. So what sort of attack vectors that we are catching? We are catching man-in-the-browser injections, malicious and compromised extensions, third-party libs, CDNs that have been compromised. And this has a very important note, provided that they inject something in the page. So this is how we catch it. If they don't do an injection, if they are just silently collecting information from the browser, then we won't see anything and we won't be able to catch it. But this is not the common scenario. We usually see that attackers they want to do stuff to the page. They want to add more JavaScript. They want to do this. They want to do that. And once they do that, we are able to help in all of these attack vectors. XSS as well, if they just manage to modify, inject a script tag, and inject some sort of inline JavaScript, we can catch that. We can see requests going out to third-party websites. And we can also detect if the user is doing the tampering himself, so like opening the Chrome DevTools and just modifying the DOM and just running stuff that modifies the DOM. We can also catch that. And usually they use these attack vectors to do what? To trick the user into do something, like give me your two-factor authentication token, to serve an exploit kit, to exfiltrate credentials, keys, data, to do form jacking, to do customer journey hijacking, which is a very funny case where, especially for e-commerce websites, when they just like place an ad just next to the price of the product, and they tell you like, hey, you can buy this product in a different website, like 10% cheaper. And that drives away the client, and it basically costs millions for the websites, from the retail websites, and it's actually happening a lot. We also have supply chain attacks, which is what we call dependencies being modified. So it's like going for the weakest link, right? If the bank has like good security measures, but somehow is including a third party, then the third party probably won't have like a very specialized security team. So we might as well just attack the weakest link, right? So we call this the supply chain attacks. We can inject ads, forms, and do cryptojacking, which is basically stealing the CPU of the end user. So concluding, the client side is the danger zone, so you can tamper with everything, you can modify everything. There's lots of ways of just ensuring that you can do that. I always say use every solution that you can. Just use defense in depth, use CSP to try to prevent XSS from executing in the page, from requests from going out. Just try to reduce the attack surface as much as you can. But in the end, those defenses, or some of those defenses, have their weak spots. For instance, everything that relies on HTTP headers can be stripped off by extensions or by manual browser Trojans. And because of that, we have just to assume that some injections will go through, and we have to have a plan to catch them. So we propose this approach, like application real-time monitoring. It won't prevent the injections, but it can help mitigate the problems that they create, right? And it's important to do this in real time. It's important to implement reaction policies. And this works even for 0 days, because we just follow a whitelisting approach. We detect any modification. And it allows you to see exactly what the user has saw. It allows you to do your own investigation. It allows you to understand what's hitting your website. And this is very hard because we are talking about the client side. And usually you just assume that if it's not hitting the server, it doesn't exist. And in my opinion, it's not the correct way that you should be thinking about protecting your web application. And you can deploy the customized reactions. And like I said, if we keep raising the bar for the attackers, probably they will just move on to the next website. And so ultimately, you can see this as a fraud mitigation or fraud anti-fraud solution for the website for this particular set of attack vectors. So this is all I had for today.